Welcome to section 16.1. In this chapter, we are going to be seeing the culmination of all of the work we have done through Calculus 3 involving partial derivatives, multiple integrals, functions of multiple variables, vectors and vector functions. All of that is coming together to give us the concept of vector calculus. In 16.1, we're going to introduce the concept of a vector field. We're going to see what that looks like, draw some examples, and look at some more new terminology that we're going to be seeing throughout this chapter. So we're going to let D be a set in R2, a vector field on R2 is a function, capital F. So I know it's kind of hard to tell. This is bolded, so it's bolded like a vector. So this is kind of like that, right? With our arrow notation that assigns to each point in xy in that domain a two-dimensional vector f of xy. So the best way to picture a vector field is to draw the arrow representing the vector f of xy starting at the point xy. So if we have, like, here's the xy plane, we have just some random points throughout the plane here. So these would be the points xy. The vector field would consist of all of the vectors that correspond to these points. However they may look, okay? So each point in the domain gets assigned a vector. And of course, when we're drawing this, we can't draw literally every single vector. We would just pick a representative sample of points to get the general idea of how the vector field moves, how it flows through the plane. Since f of xy is a two-dimensional vector, we can write it in terms of its component functions, p and q. So we say f of xy is equal to p of xy I plus q of xy j. Okay. Or if we like the component form better, so that's p of xy in the first component, q of xy in the second. But we will often use just the shorthand of f equals pi plus qj. Right? So we have here, a vector function, right? We've got functions of x and y in the components. Notice p and q are scalar functions of two variables. So even though f is a vector, right, a vector field, p and q are not themselves vectors, right? These are just scalar functions of x and y. Oftentimes these are called scalar fields. Okay? Because if you pick a point xy to plug into p or q, you'll get out a number, right? A scalar. Whereas if you pick a point to plug into f, you get out a vector, hence a vector field. So let's take a look at an example. So we have a vector field on R2 is defined by f of xy equals negative yi plus xj. Describe f by sketching some of the vectors f of xy. So before I get to the graph over there, what we're going to do is we're going to use this rule, this formula for the vector field. We're going to pick a bunch of sample points for us to try out. And we're going to see what vector is produced when we plug in that point. So I've got a bunch down here, and I'll scroll down in just a second. But if we take the point 1, 0, for example, we plug that into here. So x is 1, y is 0. So we get 0i plus 1j. So it's just going to be 0, 1 is that vector. If we plug in the vector the point 0, 1, so we get negative 1i plus 0j. So that's negative 1, 0. Yeah. We get right? -1, 0. It's basically just flipping them and negating the first one. So we end up with 0, -1. And then we get, for 0, -1, we get +1, comma 0 for the vector. So we've got a few more in here. So we've got -2, 2. We've got -2, -2. We've got, back up on this one, 2, -2, 2, 2, 0, 3, -3, 0, 0, -3, and 3, 0. And again, I found all of these simply by plugging in the point xy into that formula for the vector field F. So, but we get all of these vectors. Now, what we would do is we would start at the point and then graph the vector from that point. So we would start at the point 1, 0, and then we would graph the vector 0, 1 using that as its starting point. So if I zoom out here, we can see the vector field for these points. So let me just kind of, so like for example, you can see at the point 1, 0 right here, we've got the vector 0, 1 coming out of it right there. Right? At the point 0, 1, we have the vector -1, 0 right there. At 0, -1, we had the vector -1, 0. And at 0, -1, we had the vector 1, 0. And then we go out, right? There's all of the 2, 2, -2, 2, -2, -2, 2, -2, and all of the 3, 0, 0, 3, etc. So this gives us a general sense of the pattern of this vector field without having to graph every single point. So we just kind of have a sample here, but we can see the general flow. It is going this way. It's kind of spiraling around like that. And the vectors in the middle are much shorter, right? Representing that it's not moving as quickly or it's not moving as strongly as it is out here, because these vectors are getting much longer. In fact, this one is 3 times the length of this. And I'm sure as we went out farther, the vectors would get longer and longer. So one of the ways to think about the vector field is think of it as like a flow of like energy, or I like to think of it as like flow of like fluid. So like the flow of water or something, like a current. So if I took like a ball and I just dropped it in the water, and this was the flow of the current of the water, the ball would start to move. It would start to follow this current, getting pushed around kind of slowly at first, but as it gets further out, it's going to start pushing it harder and faster, right? Because these vectors are getting longer. So it's going to start getting pushed around faster and harder, et cetera, as it goes. And so it's just going to kind of spiral outward as we go through. So that gives us a general sense of, how an object might move through this vector field, right? This current or the flow of this. So, and oftentimes we'll be talking about things like particle motion and such as we look at vector fields like this. So if we look at top of the next page, vector fields can also apply in 3D. So let E be a subset of R3. A vector field on R3 is a function f that assigns to each point x, y, z in E a 3-dimensional vector f of x, y, z. And we can similarly express it in terms of its component functions. So we have f of x, y, z is p of x, y, z, I plus q of x, y, z, j plus r of x, y, z, k. So just like everything else we do in 3D, it's the same general setup as 2D, but with one extra variable and one extra component, right? So we have x, y, and z in each of these, and we have I, j, and k, not just I and j, but the general form is going to be the same going forward from there. So let's take a look at an example. Sketch the vector field on R3 given by f of xyz equals zk. So I want to make a few observations about this before we actually graph it. So first thing to notice is the only component here is the k component. So what does that mean for I and j? Well, it means that I and j are both 0. So there is no, so if this is like x, y, and z, it means it's not going anywhere in the x direction or in the y direction. It's only going in the z direction, either up or down. So that's important when we're graphing our vectors. So we know that all vectors are vertical. Okay. In terms of whether they point up or down, that is where the z component comes in. The numerical value of z changes as we go up and down the z-axis. If z is positive, so if we're up here above the x-axis somewhere, so let me put a little bit of scale on this. So if we're somewhere up here above the xy plane, z is positive, these vectors will have positive values and they will point up. So they point upward when above the xy plane. And similarly, when we go down below the xy plane, z is negative, so the vectors will be negative as well. They will point down and downward when below the xy plane. Okay, so we know the direction they're pointed. We know whether they point up or down depending on where they are in 3D. And we now need to just figure out how long they're going to be. The magnitude of these vectors is going to increase as z increases, okay? Or I guess you could say as the absolute value of z increases. The further away we get from the xy plane, so if z is 1, the length of the vector is 1. If z is 2, the length of the vector gets longer. If z is 3, it gets longer. If z is 4, it gets longer. And on the flip side, when we go into the negatives, if z is -1, then -2, -3, -4, the vector points down, but it still gets longer. So we can say magnitude increases as they get further from the xy plane. And then the last thing to talk about, we've talked about above the xy plane and below the xy plane. If they're in the xy plane, z is 0, so they're all 0 vectors. So they are 0 vectors in the xy plane. So if we get just kind of a sampling of points here, so like I'll do maybe just like a little 2x3 grid here. So these would all be in the xy plane. These are those 0 vectors. If we go up 1 unit, then we get a vector that points up and has a length of 1. So like that. Okay, so these should all theoretically be the same vector, just offset of each other. Okay, so we go up 1 unit. If we go up 2 units, we're going to get vectors that start at a height of 2 and they go even longer. Okay, so we get, so we get this general idea. And then et cetera, et cetera. And it would work the same way down in the negatives. So if we went down 1 unit, we would get the same type of vectors, just pointed down instead of up. So it's basically symmetric about the XY plane. Okay, and then we would get the longer ones down here. All right, so this is generally speaking what that vector field would look like. So again, if we were to take, like a ball or something, picture this is almost like a wind tunnel with a fan in the middle that's pointing both directions. Okay, so like it's taking in the air and then it's blowing it out in opposite directions depending on what side you're on. So if I toss like a ball in here, it's going to get sent that way and it's going to get faster and faster and faster as it goes up. Same thing, if I drop it down here, it's going to start dropping faster and faster and faster as we go. Theoretically, if you dropped it right on the XY plane, it wouldn't go anywhere. Okay, if it was perfectly situated on the XY plane, it would not go up or down. It would just stay exactly where it is. All right. Some examples of vector fields. There are many in different applications in like physics and engineering in particular. Velocity fields, so that's kind of what we've been talking about here in my examples. Gravitational fields, so working with the force of gravity, forming a vector field around the Earth. Force fields, electric fields, so if you're going to like electrical engineering, you'll be working with electric fields a lot. But there's one particular type of vector field that we need to talk about, and that is a gradient field or a gradient vector field. So we need to think back to a couple chapters ago when we learned about the gradient vector. So the gradient of a scalar function, so this is grad f, right, or del f of xy is equal to fx of xy I plus fy of xy j, right? It's just the vector whose components are the partial derivatives of the function f. Now, if we look at the way this formula is set up, this is exactly the same type of formula as the vector fields, right, that we just saw back up above. So grad f is really a vector field on R2, and it is called a gradient vector field. So similarly, we can work in R3 as well. So we have fx of xyz with I plus fy of xyz with j plus fz of xyz with k. So we can work in R2 or in R3. Okay, but the gradient vector field is just the gradient. Okay, it's the gradient that we're used to, but now we can apply it to any number of points in a domain, not just one point at a time. Okay, so if we look at the example on the next page, so we have a big graph here. Find the gradient vector field of f of xy equals x squared y minus y cubed. Given the plot of the gradient vector field together with a contour map of f, determine how they may be related. So first thing we can do is we can find the gradient vector field. So we're going to get grad f of xy equals So it's going to be fx and fy. So fx, that's going to be 2xy minus nothing. And fy, we get x squared minus 3y squared. So that's our gradient vector field. So if we pick any point xy in the domain, which in this case would be all of R2, we can output a vector from that. And that's what all of these little blue vector marks are here. Some of these are so tiny that you can barely see the arrow pointing, but they're in there. So there's a few things that I want to talk about when it comes to the relationship between the gradient vector field and the level curves. There's two main points to make here. The first is the physical relationship between the curves and the vectors. So specifically like the angle between them. If you look at any one of these vectors here, notice that the vectors are cutting through the level curves here, right? And it doesn't matter which ones I pick, they all do it, right? They all cut through the level curves. This is a definitive relationship. It turns out the gradient vectors are perpendicular to the level curves. Okay. So the gradient vectors are perpendicular to the level curves. They cut through the level curves. So what that means is they're giving us the steepest increase or decrease, which if you recall, back in the chapter where we talked about directional derivatives and we were finding maximum and minimum values for the derivative, we determined that the maximum derivative or maximum rate of change occurred in the direction of the gradient, right? And the actual maximum or minimum value was the length of the gradient. So the max derivative occurs in the direction of grad f. And think about what these level curves mean. The level curves are changes in altitude, changes in height. So like as we go from here to here and then to here, the height is changing, right? It's increasing or decreasing. And what the level curve is doing is, if the height is going from here to here to here, the gradient is not kind of meandering around these level curves. It's cutting straight through them. And it is going as steeply as it possibly can through those level curves. Okay, so the gradient vectors do go perpendicular to the level curves because they're giving us that maximum rate of change in that direction. The other thing to take note of is not just their position, but also their length. Notice that the gradient vectors get longer as the level curves get closer together. Right, so notice these level curves right here that are all pretty tightly grouped. See how long that gradient vector is? Whereas out here, kind of in no man's land, these are really tiny little gradient vectors because there's not a lot of level curves. It's very flat. And remember, again, that maximum rate of change is occurring in the direction of the gradient vectors. So if the level curves are close together, it's very steep. If the level curves are far apart, it's very flat, right? Very shallow. So again, recall close level curves mean steep. So high rate of change. Okay, so a very high value for the derivative, which that directional derivative for grad f is the maximum rate of change. Okay, so we would get a large value and a large length, large magnitude. All right, so these are a couple of the major ways that the gradient vector field interacts with a contour map, with the level curves for a function. A little bit of terminology here that we're going to be seeing later on in the chapter. We say a vector field F is called a conservative vector field if it is the gradient of some scalar function. So a vector field is called conservative if it is the gradient of some scalar function. So that is to say that the vector field F equals the gradient of little f. Okay, so if our vector field can be written as a gradient, it is what we say conservative. Okay? In this situation where we have a conservative vector field, little f is called a potential function of f. A lot of the properties that we're going to be using in this chapter involve conservative vector fields. So we're going to be looking at how we determine whether or not a vector field is conservative, what that exactly looks like, how to find conservative vector fields themselves, how we use them to get a lot of properties in vector calculus. So note, not all vector fields are conservative, but they do come up a lot. So we will be working with them a great deal. And again, later in the chapter, we'll learn how to determine if a vector field is conservative or not. So we're not going to use this exactly right now, but we will see it coming up in the next couple of sections. And a lot of our properties are based off of this idea that a vector field can be written as a gradient. So we'll explore that a little bit more in the upcoming sections, but that brings us to the end of section 1.